Welcome to our first video for lesson 10.6. In this video, we will be talking about the direct comparison test, which is also sometimes called the comparison test. The comparison test states the following. Let 0 be less than a sub n be less than or equal to b sub n. Now there are two parts to the direct comparison test. We have the first part and the second part. The first part states that if the series from n equals 1 to infinity of b sub n converges, so if the series defined by this function converges, then the series from n equals 1 to infinity of a sub n is also going to converge. Now, this makes sense if we think about it, because this is the smaller one and this is the larger one. If the larger one converges, then the smaller one must also converge. We would never have a situation where the smaller one would be diverging, but the bigger one would be converging. That wouldn't make sense. Now, we also know that if the smaller one, a sub n, diverges, so say this one is diverging, then the one that's bigger than that must also be diverging. The series from n equals 1 to infinity of b sub n must also be diverging. And then just a couple of notes about that. Let's say that we have the series from n equals 1 to infinity of a sub n. If we know that this smaller one is converging, we don't necessarily know what's happening with this. Because our bigger one, it could be converging to a bigger number, or it could be diverging. So we could not determine the convergence or divergence of that series from n equals 1 to infinity of b sub n. And similarly, if we have the series from n equals 1 to infinity of b sub n, and we know that that diverges, well, we could have a sub n also diverging, or we could have a sub n converging to a smaller number. So we can't determine convergence or divergence for a sub n. Let's take a look at some examples. We're going to determine the convergence or divergence of each series. First, we have to think about what is a potential series that we could compare this to that looks similar to this, or that behaves similarly to this one. Well, we're going to compare this to the series 1 over 4 to the power of n, because this series is almost 1 over 4 to the power of n. We just have that plus 6 on the end, and in the long run, that's probably not going to do a lot. So now let's set up that inequality for 0 being less than a sub n being less than or equal to b sub n. So which one is going to be greater? Is it 1 over 4 to the power of n plus 6 or 1 over 4 to the power of n? Well, if we have 1 over 4 to the power of n plus 6, that denominator is going to be greater than the denominator of a plane 4 to the power of n. And if the denominator is bigger, that means you're dividing it by a bigger number, so the actual thing is going to be smaller. So this is going to be less than 1 over 4 to the power of n. So now we have our inequality set up just like we did in this first one. So we have 0 less than a sub n less than or equal to b sub n. Now, if this one, the series of 1 over 4 to the power of n, if that one converges, we can say that this one also converges. Because if our bigger one converges, then the smaller one must converge too. But if this one diverges, we're not going to be able to get a lot of information about this one, because it could converge to a smaller number, or it could also diverge. Well, if we look at this one, if we have the series from n equals 1 to infinity of 1 over 4 to the power of n, we can rewrite that one as the series from n equals 1 to infinity of 1/4 to the power of n. And we know from our knowledge about geometric series, which I do have a separate video on if you're interested in reviewing that, when our r value, which is the 1/4, or when the absolute value of our 1/4, which is the absolute value of r, is less than 1, that means that our series is going to converge. So if this one converges, we know that this one is going to converge too. Now I'm just going to write out a brief explanation. This series converges by direct comparison, because it's the direct comparison test, with the series from n equals 1 to infinity of 1 over 4 to the power of n, which converges. Let's try our next one. We have 1 over 3n squared plus 5. And we're trying to find something that is going to be similar to this, but maybe just a little bigger or a little smaller than that. So if we have 1 over 3 to the 3n squared plus 5, now what's something that's similar to that? Well, what if we had 1 over 3n squared? Or what if we just had something like 1 over n squared, because that's even easier. And we know by the p-series test that 1 over n squared is going to converge. So we will compare this to 1 over n squared. Now we have to figure out, is 1 over n squared going to be less than or greater than this function? So if we have 1 over 3n squared plus 5, that's going to be a bigger denominator than 1 over n squared. Bigger denominator means smaller function. So this is going to be less than 1 over n squared. And they are both greater than 0. So now we have our inequality set up. So again, remember we know that 1 over n squared is going to converge by the p-series test. So if this one converges, that means that our bigger function is converging. So the function that's smaller than that must also converge. This one could not possibly diverge. So we're going to say that this series converges by direct comparison with the series from n equals 1 to infinity of 1 over n squared, which also converges. Let's try a third example. We're still trying to determine the convergence or divergence of the series. What's something that we could compare this to that's very similar to our original a sub n expression right in here? Well, if we have 1 over 3 to the power of n minus 2, that is almost the same thing as 1 over 3 to the power of n. So then we have to think about which one of those is going to be greater. If we have 1 over 3 to the power of n minus 2, that means that our denominator got a little bit smaller. So we're dividing by a smaller number, which is going to give us a bigger number overall. So that one is going to be bigger than 1 over 3 to the power of n, and then both of those are going to be greater than 0. However, the problem here is that if we take the series from n equals 1 to infinity of 1 over 3 to the power of n, we know that that one's going to converge because that acts like the geometric series 1/3 to the power of n, and the absolute value of our r value, 1/3, is going to be less than 1. So this converges. So if this one converges, then we don't know what's happening with this. This one could be converging or it could be diverging because we could have it converging to a bigger value than this, which would make this statement true, or we could have this one diverging. So we're actually going to have to pick something else to compare this to. What if we chose instead to compare this to 1 over 2 to the power of n? If we have 1 over 2 to the power of n, 2 to the power of n, that's going to be growing slower than 3 to the power of n. So 3 to the power of n is going to have a bigger denominator, which means a smaller function. So we could set up our inequality like this. 0 is less than 1 over 3 to the power of n minus 2 is less than or equal to 1 over 2 to the power of n. So now we just have to figure out what's happening with the 1 over 2 to the power of n. If we have the series from n equals 1 to infinity of 1 over 2 to the power of n, that one is the same thing as series from n equals 1 to infinity of 1/2 to the power of n. Now, because the absolute value of our r value, which is equal to the absolute value of 1/2, or 1/2 is less than 1, that means that our series is going to converge. So that means this series converges. If the bigger one converges, the one that's smaller than that must also be converging, because converging means that it's smaller than if it's diverging. So we will say that this series converges by direct comparison with the series from n equals 1 to infinity of 1/2 to the power of n, which also converges. There's my response. Which of the following series can be used with the comparison test to determine whether the series from n equals 1 to infinity of 8 plus cosine n over n cubed converges or diverges? A couple of things to note. When we see the comparison test, that means direct comparison, not limit comparison, which we'll be talking about in a future video. So let's try setting up this first one. We have to figure out which is greater, 7 over n cubed or 8 plus cosine n over n cubed. Well, if we have 7 over n cubed, yes, that one is going to be less than 8 plus the cosine of n cubed. And that's always going to be true, except for times when we have cosine of pi, because the cosine of pi is equal to -1. So if we have 8 plus -1, that's going to be equal to 7. However, we know that it's okay if we have that less than or equal to, because this is setting it up as 0, less than 7 over n cubed, less than or equal to 8 plus cosine n over n cubed. So then what we have to do is determine, does this series of 7 over n cubed, is that a converging or diverging series? Based on our value of p, which in this case is 3, and we can even use the p series when we don't have a 1 on top, we can still use that test, this series is going to converge. However, this is a problem because if we have something that is greater than a converging series, that doesn't give us a lot of information about the convergence or divergence of the series. If we have a diverging series over here, that could be very, very possible. If we have a converging series, that can definitely be less than a diverging series. However, we could also have it converging just to a larger value than this one. Therefore, we cannot use choice A. Even though we can set up the inequality, it doesn't work because this middle one converges. So how about if we have 8 over n cubed in the middle? Well, if we have 8 over n cubed in the middle, we cannot say that that one is always less than or equal to 8 plus cosine n over n cubed. Because if we have something like the cosine of pi, remember cosine of pi is -1. So 8 plus -1, well, that's 7. And 7 is not greater than 8. So that is not true. Let's check out option C. In this case, we have 9 over n cubed. So in this case, the 9 over n cubed is actually going to go on this side because that is always greater than or equal to 8 plus cosine n over n cubed, which is also greater than 0. Because the maximum value of cosine that we would have is a 1. Cosine of 0 is equal to 1. Cosine of 2 pi is equal to 1. So if we have something like 8 plus 1 over n cubed, that's the same as 9 over n cubed. And we can have that one being equal, as long as it's greater than during the other times. So this one, we would have 9 over n cubed, and this one is also going to converge by the p-series test. So if this one is going to be less than a converging series, anything that's less than a converging series is also going to have to converge to some value. We couldn't have this one diverging because then it would not be less than or equal to 9 over n cubed. So this one is true, and we can use this with the comparison test to determine that this series in fact converges. Which of the following series can be used with the comparison test? And remember, the comparison test means the direct comparison test, to determine whether the series from n equals 1 to infinity of 1 over n squared plus 9 converges or diverges. For this one, I already have a pretty good idea of what I might be comparing this to. If I have 1 over n squared, then I would just have to position the 1 over n squared plus 9 on the correct side. 1 over n squared plus 9 is going to be less than 1 over n squared because we're adding something to the denominator. Bigger denominator means smaller function. So 1 over n squared plus 9 is going to be less than or equal to that, and we have the 0 on this side. Then, due to the p-series test, we know that this series here is going to converge. So if this one converges, that means that this one is also going to converge. And what it was really asking us is which of the following series can be used. So it's the series from n equals 1 to infinity of 1 over n squared. That is the one that we used. So choice A is correct here. Which of the following statements about the convergence or divergence of the series from n equals 1 to infinity of 1 over the natural log of n plus 1 is true? It says it converges by comparison with one of these, or it diverges by comparison with one of these. First, I want to think about what the graph of the natural log of n plus 1 might look like. So normally the natural log of n would pass through the point 1, 0 because the natural log of 1 is equal to 0. However, since we have moved it to the left 1 unit, we have that n plus 1, which gives it a horizontal translation over 1 unit. We're going to be passing through the point 0, 0. But it's still going to have that general same shape of the natural log graph, which is going to look something like this. Now, in relation to our other denominators here, we have n or n squared. Just a plain n would look like this. And the graph of n squared would look like this. So based on this graph, it looks like if we have a plain n, or y equals x, you could think of it like that, that's going to be greater than the natural log of n plus 1 always. So how does this apply back to our problem? Well, if we have 1 over the natural log of n plus 1, we're trying to set up some kind of inequality where this is less than or equal to something else. Or maybe where something else is less than or equal to this. And we know what those somethings are going to be. It's going to be 1 over n or 1 over n squared. I'm going to test 1 over n first. If I have 1 over n is less than or equal to 1 over the natural log of n plus 1, this makes a lot of sense because looking over here at the graph of y equals n, or you could think of it as just a plain y equals x, that n is always going to be greater than the natural log of n plus 1. Bigger denominator means smaller overall function. If we have something like 1/10, that's going to be less than 1/3. So this statement right here is true. And then we're just going to stick the 0 on the beginning. Now we have to think about what this means in terms of whether it converges or diverges. We know that if we have the series from n equals 1 to infinity of 1 over n, that is the harmonic series, and that is going to diverge. So if this one diverges, and we have some series that is greater than a diverging series, this other series must also diverge. We know that this graph is always going to be greater than a diverging one. So if this one diverges, this one also needs to diverge. So we can say that answer choice C is correct. This series diverges by comparison with the series from n equals 1 to infinity of 1 over n. Consider the series from n equals 1 to infinity of c sub n and the series from n equals 1 to infinity of d sub n, where c sub n is greater than 0 and d sub n is greater than 0 for n being greater than or equal to 1. If c sub n is less than or equal to d sub n, then which of the following must be true? The way that I'm going to set this one up is I'm going to say 0 is less than c sub n is less than or equal to d sub n, so that I can use my direct comparison test. And I know that that 0 is true because we know that c and d are greater than 0. The first one says if c converges, so if this converges, then d converges. Is that true? Well, we could have this one converging, the smaller one converging, and then the bigger one converging to a bigger number, or we could have the bigger one diverging. So this one is not necessarily true. D could be diverging in this case. The second one says if C converges, so if this one converges, Well, then we don't know about d sub n. We don't know if this one is going to converge or diverge. That's the same thing that we were just talking through with A. So we don't know about that one. What about choice C? If C diverges, so if this smaller one diverges, then the one that is greater than that must converge? No, that doesn't make sense. That's the opposite of what we would think. Now, if C diverges, if this smaller one diverges, then the bigger one must also diverge. That is true. Which of the following series converge? We'll be using a variety of different tests in this problem because they're giving us a variety of different series. First, for number 1, let's try the nth term test. Let's see if we could prove that it diverges. So for the nth term test, we take the limit as n approaches infinity of a sub n, which in this case is the natural log of n plus 3 over n. Now, originally, we're going to get infinity over infinity, but what we can do is use L'Hopital's rule, take the derivative of the top and the bottom, and we have limit as n approaches infinity of derivative of natural log of n plus 3 is going to be 1 over n. Derivative of n is going to be a plain 1. Now, if we plug in infinity up here, we'll have 1 over a huge number, which produces a 0 in the numerator. So this is equal to 0. If the limit as n approaches infinity of a sub n is equal to 0, the nth term test is inconclusive, which means that we need to try another test. Let's see if we could potentially use direct comparison. Now, the graph of the natural log of n plus 3, or y equals the natural log of x plus 3, is going to look similar to the overall shape of the natural log graph, but this plus 3 inside the parentheses moves it over 3 units to the left. So it's going to look something like this. So what's something that we could potentially compare this to using direct comparison? Well, what if we said 1 over n, and we compare that to the natural log of n plus 3 over n? Looking at this graph of the natural log of n plus 3, y equals 1 is going to be right around here. And if we are starting our series at n equals 1, that means that we're going to have to come up with some inequality between these two graphs that's going to have to be true for x being greater than or equal to 1. So just looking at the graph of 1, because we're just going to really be comparing the numerators here, and the denominators aren't going to do much because those stay the same, 1 is always going to be less than the natural log of x plus 3 or the natural log of n plus 3 for the numbers that we care about. So we're going to set this inequality up like this. 0 is less than 1 over n is less than or equal to the natural log of n plus 3 over n. Now let's think about what happens if we have the series from n equals 1 to infinity of 1 over n. That's the harmonic series, so that's going to diverge. So if we know that this one is going to diverge, if we know that the smaller series diverges, anything that's bigger than that diverging series is also going to have to diverge. So we know that this one, the natural log of n plus 3 over n, that series is going to be diverging. Therefore, since it is not converging, we're going to cross off answer choice 1. Time to figure out whether number 2 converges or diverges. Again, the nth term test is probably my favorite test because that's the easiest and the simplest, and it can get you a really quick answer to determine if your series diverges. So let's take the limit as n approaches infinity of a sub n, which in this case is 3 to the power of n over 4 to the power of n plus 5. Over time, we're going to have 3 to the power of n growing at a slower rate than 4 to the power of n, so this one is going to be equal to 0. So unfortunately, because we do get a 0 here when using the nth term test, we have to pick another test. Let's see if we could potentially use direct comparison for this one. If we have 3 to the power of n over 4 to the power of n plus 5, that is pretty close to 3 to the power of n over 4 to the power of n. Now, 3 to the power of n over 4 to the power of n is going to be slightly greater than 3 to the power of n over 4 to the power of n plus 5, because making that denominator a little bit bigger when we keep the numerator the same is going to make our overall function a bit smaller. So we'll set up our inequality like this. Now, could we figure out whether the series from n equals 1 to infinity of 3 to the power of n over 4 to the power of n converges or diverges? Yeah, we can use the geometric series test. I do have a separate video on that if that's something that you need to review. This can be rewritten as the series from n equals 1 to infinity of 3/4 to the power of n. And this one is going to converge because the absolute value of 3/4 is less than 1. So if we know that this one is going to converge, that means that the bigger series is converging. So a series that's smaller than a converging series must also be converging. That we are using the direct comparison test there. Therefore, we know that number 2 is going to converge. Now let's try number 3. We have the series from n equals 1 to infinity of 1 over 4n. I'm not going to want to use the nth term test here because I know that if I plug in an infinity right here, I'm going to get 1 over a huge number, which is going to be approaching 0. And when we get a 0 for the nth term test, that's inconclusive. So we're going to have to try a different test here. Now, this series actually involves using something called the limit comparison test, which we have not covered yet. That is in the next video for 10.6, part 2. So if that's something that you want to watch before this, or if you just want to skip over this part of the problem, that's completely fine. In order to use the limit comparison test, we're going to have to come up with a similar series that we can compare this to. We're going to compare this to the series from n equals 1 to infinity of 1 over n. Now, the way that we handle the limit comparison test, in order to determine whether the behavior of this series and this series are the same, we need to take the limit as n approaches infinity of our original a sub n, which is 1 over 4n, and then we multiply it by the reciprocal, or we divide it by our new a sub n, which is 1 over n. So we divide by 1 over n, that's the same thing as multiplying by n over 1. And we get, let's see, the n's are going to cancel up here, and we get 1/4. So since this is a positive finite number, that means that we can conclude that the behavior of this series and this series are going to be the same. Since this one diverges, this series is going to diverge because that is a harmonic series. We know that this series is also going to diverge. Since number 3 diverges, it means that it does not converge. Therefore, B is correct. Only series 2 is going to converge.